We would like to express our gratitude for the organization committee for this opportunity, and I would like to thank all the participants for being here. My name is Pekeriçli Özel, and as you can see, the title of um, our study is Generation and Evaluation of High-Fidelity Virtual Twins and All-Inclusive Pipeline for Enhanced Construction Efficiency in Diverse VR Environments. This study is a collaboration, an international collaboration between Politecnico di Milano, Gicarus Lab in Politecnico, Middle East Technical University, and Ankara Yıldırım Beyazıt University. And it is partially supported by TÜBİTAK Scientific Council. So let's start with a simple outline of the presentation. I will first give some introductory information about the study, and then one by one we will move over each step in the pipeline with help of a case study and end up with extended reality. So before anything else, let's take a quick look at the research method, which is more or less actually the summary of the study. You can see we basically have four main steps in the suggested pipeline. Right now, I will just give you a quick glimpse, and in the upcoming stages of the presentation, I will go over them one by one. And let's go over the problem statement of the study. So we all are aware of the ongoing adoption of advanced digital surveying in the construction industry. We have seen many great presentations about this adoption, and it is becoming more and more apparent each day, as we all know. And this digital surveying tools provides us with a vast amount of data. But on the other hand, this data by itself is not very much meaningful. It needs to be represented in a useful way. And this is where extended reality systems come into play. Digital twins and scan to XR systems are pivotal in that regard because they are the link between the data from digital surveying and the representational power of extended reality. However, this is not an easy thing to do. As we all know, it's a very complex process that requires expertise in various domains and prowess in, let's say, several software at the same time. And on top of these hardships, since we are talking about virtual reality, which is inherently power hungry, and we also aim for some mobile devices like smartphones, standalone HMDs or tablets, we need optimization of these models. So more or less these last three bullets are the main goal of the study, to provide a pipeline, a workflow that will work as the link between the data of the digital surveying and representational power of extended reality in a sustainable, accessible, easy to implement, and efficient way. This is the main goal. And let's quickly take a look at our pipeline again, but this time with these added goals. So we have, as I said, model optimization. And in this pipeline, it is broken down into two parts: mesh optimization and texture optimization. And then as the expected results of this kind of a pipeline, we can say an immersive and realistic visualization, immediate feedback and interactivity between the parties involved in the process, reduction of errors and misunderstandings throughout the design and construction phases, an improved decision-making process, especially in the design phase, and finally, of course, an increased client engagement and, as a result, an increased client satisfaction. So all these things, we think, can be achieved with information-rich, easy to use, easy to access, high quality and interactive XR visualizations. So naturally, the first step in this kind of a pipeline is data collection. We collect data about physical conditions at the site, which includes, of course, structural and architectural elements, but also ongoing works, available equipment, and site conditions. And for this, the pipeline suggests two forms of digital surveying: digital photogrammetry and laser scanning. And in our case study, we have implemented terrestrial laser scanning, and 2 to 3 scans were carried out for each room. Of course, if it is needed, more can be done, but for our case study, it was enough. And in this slide, you can see a photograph and a screenshot from the laser scan point cloud of the same area in our case study. And the second mode of digital surveying included in the pipeline is photogrammetry. And during the case study, we used around 500 photos of each room. Photogrammetric data was used for both the model geometry and also the textures of the model. And being able to provide high fidelity textures makes photogrammetry a crucial tool for this pipeline. So after the data collection phase is over, we move on to the second phase of the pipeline, which is generating the initial model. This model includes structural and architectural elements, and as I said before, it also includes ongoing works and site conditions, equipments, and whatnot. And generating this model in a single take is not feasible. So several smaller models were generated independent from each other, and those different smaller parts were connected to each other. They are connected to each other with the help of laser scanning data. The problem of this initial model is that, yes, it is precise, it is detailed, but it also has a colossal processing cost. So it is not very much suitable for extended reality because we already aim for some mobile devices and we don't have a lot of processing power. As a matter of fact, in our case study, the model had more than 6,000 polygons. So naturally, it needs some optimization, mesh optimization. And which brings us to first of two optimization types suggested in the pipeline, the mesh optimization. Of course, there are lots and lots of ways to optimize the mesh model, but as I mentioned in the very beginning, one of the objectives of this pipeline is to keep things as simple and as accessible as possible. Therefore, instead of hopping within several software like Blender and Substance Designer and some other very commonly used mesh optimization software, we tried to come up with an optimization method that can be done directly in a photogrammetric software, which in our case study is Metashape. And this mesh optimization is, of course, less effective, but it's much more simpler than a mesh optimization done in a 3D modeling software like 3ds Max or Blender. Basically, the idea is to focus on the flat surfaces. To be able to reduce the number of polygons as much as possible in a simple way, because as you know, flat surfaces allow you to reduce polygon count without significant changes in the geometry of the let's say surface. And let me explain it with a very simple example. Let's assume that we have a 6-vertex surface. So typically, after photogrammetric modeling, we end up with this kind of a surface, a surface that is modeled with a lot of polygons. But theoretically, this kind of a 6-vertex surface can easily be modeled with only 4 polygons. And as you can see, the one on the left and the one on the middle are exactly the same in terms of geometric information. Which shows us why focusing on flat surfaces is a good idea, because the number of polygons can be reduced without much effort and without losing any kind of geometrical information. And in our case study, using this and only this optimization technique, we were able to reduce the number of polygons in the model from over 6,000 to a little bit higher than 35,000 at the end. And you can see some screenshots of the of before and after mesh model optimization. On the left, you can see there are a lot of polygons, and on the right, after some optimization in the flat surfaces, the number of polygons are not ideal, but much lower than the original one. And at the bottom, you can see the final result with the textures are almost exactly the same, even though the number of polygons are much, much lower. And after the mesh optimization is done, we start with some model interoperability options. Of course, this stage is a little bit project dependent. So according to available resources and required knowledge in the information, required information in the project, several models can be generated. They can be transferred to BIM and can be used in different stages of construction and commissioning process. For example, in our case study, there was a vaulted ceiling, and we needed a precise model of the ceiling to be able to make the final decision regarding the finishing to be applied to the ceiling. And with the help of the model we have, we were able to measure the deviation between the model and the scan. And as you can see here, the final result was a very precise model with a standard deviation less than 2 millimeters. And also, as an added benefit, having this kind of a very precise model means it would be easier to get building permits when they are needed, because you have a very precise model to show. Or after, let's say, you have an accurate model, it becomes possible to link it with project schedule to plan and adjust work sequences, or let's say workforce planning in a more informed way with less mistakes. And after that, we move on to the real-time development platform stage, which is the one before the final. And the goal here to make the model interactable and ready for XR. But before extended reality, we need one more type of optimization, and it is a texture optimization. For texture optimization, the pipeline suggests two techniques: MIP mapping and anisotrophic filtering, and I will quickly explain what they are in a second. And after the texture optimization is done, several models of the XR environment can be generated as needed. It can be different stages of the construction, or various versions of the model can be generated for PC, mobile devices, or VR headsets. So MIP mapping, I will very quickly explain it without going into much detail. It means MIP mapping is a technique of generating smaller versions of the same texture, so that when the viewer is away from the object, the small version of the texture can be used. For example, the MIP 0 is the original texture, and when the object gets a little bit away from the camera, we use MIP 1, which is the half of the MIP 0. And when it gets more further, we use MIP 2, and this goes on. This slightly increases the size on disk, but it really lowers the load on the GPU. So we can easily say it's a very beneficial technique. And as an added benefit, it also eliminates some visual artifacts. So you both reduce the GPU load and also increase the visual quality of the XR environment. And the second technique used in the pipeline is anisotrophic filtering. Anisotropy is stretching a texture in different ratios for different axes. It is like you have a texture and you stretch
Please,
it in different
please, the
angles.
time is over. Please finish the
Okay, I need
presentation.
just one more minute because this is the one before the last. So, and in anisotrophic filtering, you, instead of stretching it real time, you use some pre-stretched versions of the textures. Let me quickly, and in case study, we used as 16x anisotrophic filtering. And on the left, you see no filter, and on the right, you see with the filter. And in large screens like VR environments, this makes a huge difference. And finally, we end up with extended reality phase, which is the final phase. Um, you can see a lot of different versions of the same model can be generated for mobile phones, for laptops, PCs, for head-mounted displays, and also different versions were generated in the case study with the help of the pipeline for different stages of the construction, like the early works in the construction or as designed version. And all of them were helping to to have a better, more efficient communication between different parties and better planning and better decision making. So this was the last slide of my presentation. Thank you very much for listening, and I'm sorry that I went just a little bit over the time. So thank you. The video will end in a second, and I will conclude my presentation.
Okay. Thank you. Thank you so much for the very
Thank you.
presentation, and thank you for sharing these very interesting research topics.